Okay, so thank you. Really fun to be here, having a great time. So I'm going to tell you about delegating computation in application to PPAD. This is joint work with my student Lisa Yang and Omer Panet, who was a postdoc with us. Okay, so let me start. By the way, feel free at any point to ask me questions, okay? So it should be interactive. Okay, so here's the problem we're studying. Suppose you have like a smartwatch, a very weak computational device that wants to do a heavy computation. So suppose he wants to run a time t computation, some Turing machine on input x, and the runtime is t, but he's weak, he cannot do it on his own. Okay, so what's the goal? The idea is you want like a cloud provider or some powerful device to do the computation for him. But now suppose he doesn't trust the device. So the goal is, what we want is for the powerful device or the cloud to provide a proof, pi, that indeed this is the correct output of the computation. And therefore we think of the weak device as a verifier who verifies this proof, and the cloud provider as the prover, or the powerful party is the prover. And of course the goal is, we want verification to be very efficient, and particularly much more efficient than time t, because then he would do the computation on its own. So this is the basic question, exactly this. Can verifying, or is verifying easier than doing the computation? Okay? So this is exactly the problem we're studying. And this problem already was studied actually starting from the work in interactive proofs in the mid-'80s, where they asked, what is the power of proving? And this was, it was shown by the seminal work of Shamir that IP equals P space. In other words, you can efficiently verify really long computation, t-time computation, where the time of the verification is s, like the space, more or less. So if you have a very long computation and the space is small, you can verify it efficiently. Okay? However, this is not good for us. And the reason is the runtime of the prover in this setting, at least in these seminal works, he was really not efficient. So his runtime was 2 to the space squared. So even if you think about efficient computation and even log space, he runs in super polynomial time. Okay, so the problem that we started studying already many years ago was, how about if we want doubly efficient proofs? What do we mean by doubly efficient? Well, as before, we want the verifier to be super efficient, run in time much less than t, but we also add a restriction on the prover's efficiency, which kind of the classical works did not impose. Okay, so we just add a restriction. What if we want the prover's runtime not to blow up by too much, only to have a polynomial blow up? And even in this setting, we have some results. So we have a joint result with Shafi, Goldwasser, and Guy Rothblum, where we showed, this can be done, doubly efficient, but where the verifier's runtime grows with the depth of the computation. So when we talk about depth, we think of the model of circuits as opposed to Turing machine. And then afterward, there was a breakthrough result by Reingold and the Rothblum brothers that showed actually you can do any space S. You can verify where the verifier runs in time S, but there was also a multiplicative factor of t to the epsilon, where epsilon is a very small constant, can be any small constant. It can even be like 1 over log n, but essentially t to the epsilon. Okay, now I'll get back to this RRR result in a bit. Okay, so this is all very nice. But actually what we're interested in this work that we're doing today, that I'm going to talk to you about today, we want a non-interactive delegation scheme. So what we really forget about going back, forth, we want like a proof, like, mathematicians think of proofs, just a book where you have or some, paper, we have kind of the proof written. And can we have a non-interactive delegation scheme? And actually it's very easy to see that this is impossible. Okay, you can't take a large, under some reasonable complexity assumptions, you can't take an arbitrary long computation and kind of compress it to a short witness. We don't believe we can do that in general. But the question we study, can you do it if you resort to computational assumptions? And that's kind of where I'm a cryptographer, that's where the crypto comes in. So even though the question is there's no secrecy involved, nothing, but still the cryptography comes in. And so we show you can do that if you resort to computational assumptions and rely on some common reference string. So let me say a little bit more. So now suppose we have some common reference string in the sky. You can think of it as a hash function. You can think of it as like a product of two primes. And now, the goal is for the prover to give a proof that may depend on the CRS. And importantly, we want the CRS to be reusable. So once the CRS is in the sky, you can generate many, many proofs corresponding to this CRS for many statements. And let me say a little formally the guarantees we want from this delegation scheme. So the first, we want completeness. So you can generate a convincing proof for any correct computation. Okay, so that's the standard completeness. Soundness is slightly non-standard, and I mean to complexity theorists at least. And the notion of soundness we want to say that no computationally bounded cheating prover can produce a false statement together with a convincing proof. Okay, so if you're all powerful and you can you can factor the number in the CRS or whatever, you can cheat. But as long as you're computationally bounded and we rely on some assumption and some hardness assumption corresponding to the CRS, then we want to say, even if you see the CRS, and after the CRS you can choose whatever computation you want that's incorrect, you won't be able to generate a convincing proof for it, except for with negligible error. And with negligible error, you can also break the assumption. So, okay? So that's the soundness. And the efficiency is exactly what we said. We want the verifier to be, of course, run in significantly less time than t, and we want the prover to have only polynomial blow-up. Questions about the setting, the goal? Okay. Okay. So, moreover, another thing that we really care about, we want these proofs to be what we call publicly verifiable. What we mean by publicly verifiable is to verify this proof, all you need is really to know the CRS, the statement, and the proof. That's it. You don't need to know some kind of trapdoor information about the CRS. So for example, if this is a product of two primes, you don't need to know the two primes in order to verify the proofs. So once the CRS is set, anybody can verify the proof. Okay, all the smartwatches in the world can verify this proof. So this is our goal. Our goal is to get a non-interactive, meaning a CRS, and then just proofs, as many as you want, that anybody can verify. And the reason this is kind of became a really hot topic in cryptography is partially because of blockchain technology. Many cryptocurrencies now use these succinct proofs where they want to kind of prove that a transaction is valid. So these things are used in practice. And moreover, also there's a lot of work that actually is built based on all these theoretical works. A lot of systems are built, and the things that are actually deployed are based on these. And this is a subset. There's many more, but I'm not following up to date, so don't look too closely. And indeed, there's been a lot of prior work on this question. And let me tell you what we know. So the point is, we do know how to do it, but based on very strong assumptions. So we know how to do it based on an idealized model, which is called the random oracle model, but it's not really a real world model, so I don't want to get into it. We know how to do it based on knowledge assumptions, which essentially, they kind of, these knowledge assumptions in some way, it's pretty close to assuming that the scheme is sound to begin with. It kind of says, well, if the cheating prover has cheated, he must have cheated in this way. So we also don't like these kind of, it's not like a complexity type assumption. Another assumption is indistinguishable with obfuscation in multilinear maps. And so the assumption on multilinear map, we don't have any candidate of multilinear maps today. So we just don't have candidates for this. I/O, there's a lot of research on this topic, and hopefully it will become, based on kind of standard assumptions. But today I think we're still in this cat and mouse phase where something is assumed and then broken, and assumed and broken, assumed and broken, and it's still very shaky, this type of assumption. Okay, so the point is, all these assumptions are extremely strong assumptions, and our goal is to construct these things from kind of what we call falsifiable assumptions, in the language of Monina O. And falsifiable assumption, which none of these are, just means, you want a complexity assumption that if one can break, you can easily verify that it's broken, to get kind of this win-win thing that is very kind of the bread and butter of theoretical cryptography. They want to say either this scheme is secure, or if not, we made huge progress in understanding some mathematical problem. So this is really what we want. This is kind of being consistent with the kind of view of why theoretical cryptography is interesting. Okay, so this is the problem we solve. So here's the result in more specifically. We construct such a publicly verifiable non-interactive delegation scheme based on a falsifiable assumption. And this is an assumption on groups with bilinear maps. So here's what you don't, the truth is you don't need to look at the assumption. Most of you are not cryptographers, so it probably won't mean much to you. But essentially what it says, that if I give you, there's a group G with a bilinear group, a group with a bilinear map G. And if I give you a generator and a generator to the power of a random s squared, s to the third, blah, 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 you can't distinguish a random element from the group from a element G to the power of a high power of s. So s of at least 2 alpha plus 1. Even if you give this auxiliary information. So actually, I don't think it's important for you to go to look at exactly the assumption. For those who know a little bit more cryptography, it's an assumption that easily can be seen that it holds in the generic group model. And similar assumptions to this assumption were made before. Not the exact same, but kind of similar nature. So I'm not going to go, none of this, what I'm going to show you will actually depend on this assumption. So I just put it here for completeness, but the rest of the talk will not, it'll not come up, this assumption. And what exactly is the runtime of the verifier? So for time t computation, the verifier's runtime is also t to the epsilon for very small epsilon. So this is similar to the RRR result that I talked to you about, doubly efficient interactive proof. So we can also only get down to t to the epsilon, where epsilon can be kind of, you should think of it as a small constant or 1 over log n, where n is the input size. And this, I mean, ideally we would like to get polylog t, not t to the epsilon. And we get this kind of t to the epsilon for the exact same reason that they do. And it's some recursive reason that hopefully I'll get into. So, but the take-home message from this slide should be, we do construct publicly verifiable. So anybody can verify non-interactive delegation scheme. It's based on a new falsifiable assumption and groups with bilinear maps that are hold in the generic group model. But the verifier's runtime is small, it's t to the epsilon, but it's not as small as one can hope for, which is polylog t.
Do the I/O schemes get the optimal thing, or are they also t to the epsilon?
Okay, so they get better than t to the epsilon, but they don't get the optimal thing because things break. I don't know, they don't get the polylog t, I think the assumption is already false. I don't know how far, because they need to assume sub-exponential hardness, so they can't get it, I'm not sure.
Okay.
I'm not sure, but I don't think they can go as long, but I think they do better than t to the epsilon. Okay, any other questions? Okay, so is the result clear? At least the initial result? Okay, so because we go to t to the epsilon, and also because we use cryptography, and also because of our motivation is kind of real-world application, our focus is really on polynomial time computations. So those of you who studied kind of the IP equals P space and PCP theorems and MIP and so on and so forth, usually we think of the scale-up version. Can we do X? Can we do next? Can we do? Here, kind of come back to Earth, where usually we can only do polynomial time computations, and our goal is kind of focus on polynomial time computations, where think of the verifier, he needs to be really efficient, so he needs to run in time n to the epsilon, even if the computation takes time n to the 100. So this is kind of, I think it's, I mean, we can do it for higher classes, but I think this is the mindset you should be in. Okay, and I want to mention a really nice concurrent work of Canetti et al., where they also came up with a publicly verifiable non-interactive delegation that was only for bounded depth. And their assumption was actually that LWE has, which is a cryptographic assumption, I don't want to define it, it's just a very standard cryptographic assumption, that it has optimal security. Namely, that you cannot guess the secret with probability better than just guessing. Like, essentially polynomial over 2 to the n, where n is the number of bits in the secret. This work is really, really nice. Also, the technique there is very nice. They kind of did it by proving that if you look at this, the GKR doubly efficient proof that I mentioned, and you apply this transformation known as Fiat-Shamir, it remains sound. So this result is interesting beyond this kind of statement. Okay, but I'm going to focus on our result. And I want to mention that in addition, we have two very special properties that I think are very interesting on their own, but it's also what gives us the PPAD application that I talked about. And I'll explain what PPAD is. Okay, so what are the two special properties? The first property that we get of our delegation scheme is that it's unambiguous. And what it means to be unambiguous means that for a given computation, correct computation, you cannot generate more than one convincing proof. Okay, so there's only one proof that will be accepted. Okay, or it's hard to come up with two different proofs. Okay? And the second property is that you can update your proof. In other words, suppose you proved that some computation, you start from configuration 0 to configuration t, and you give a proof. And this is a long, long way to go from configuration 0 to configuration t. And it took you a long time to generate this proof. And now you just want to go a little further to configuration t plus 1, or a little further. You don't need to reprove everything. You just need to kind of update the proof. And the amount of work you do is only related to how much you updated it. So you can update it very efficiently. So the idea is, you can do a little proof here, give it to someone else, he'll continue to do the proof, give it to someone else, continue to do the proof, and so on and so forth. Okay, so these are the two.
What are the relations between the two programs? That one is a subset of the other? What do you mean continue?
Okay, so good. So what's needed for us, for this specific application of PPAD, you want to think of a Turing machine, like a computation that has configurations. Really think of like bounded space Turing machine.
The function that you want.
Yeah, exactly. Think if there's a really long function, but the space is bounded. That's what you should have in your head for this talk. A very, very long computation that the space is bounded. I arrived to configuration t, up to some configuration of the Turing machine. But I'm done. So now I give you this configuration, and I tell you continue. You did some configuration, you're done. You give Ran, he continues. Bernard continues. And we can kind of update the proof as we go along. That's what you should think about. But you're right, actually, our updatability is better. In other words, I can prove that, some computation like m and x1 gives y1 with a proof, but I'm not going to prove that m and x2 equals y2 in a proof, and I can combine these proofs to prove that m and x1 plus m and x2 equals y1 plus y2. So I can do these binary things. We can do more general, but the reason I wrote it this way is that's what we need for the PPAD result.
How does the space of the prover grow with the space of the computation, or? Good.
So for this, yes, the space of the prover. Now, okay, you're talking about the verifier or the prover?
The prover, because you're imagining. You said you're imagining this very low space computation, but is the prover space also small, or is the prover space?
Oh, good. We can actually preserve.
Okay.
We can preserve the prover space. Yeah, we didn't focus on it, but yeah, it can be preserved. There's no, yeah. Okay, so these are the two properties. Any question about the updatability and unambiguity properties? Okay, so what we know is that actually, this is from prior work, that if you have a publicly verifiable delegation scheme that satisfies these two properties, you immediately get PPAD hardness. And the next thing I'm going to tell you what PPAD is and what does it mean to be PPAD hard. Okay, so it's coming up in the next slide.
Hardness of what?
I'll say exactly what this means. But the point is, if you have these two, you get an interesting result that I'm going to explain what it is in the next slide. Another thing I want to point out, though, before I go to the application of these two properties, that I think these two properties are very interesting on their own, beside that specific application. So there have been delegation schemes for very specific languages that had these properties, and they showed PPAD hardness too. Their goal was to do PPAD hardness, but they could do it only for very specific kind of computations, which was enough for PPAD hardness. But I think that these two are very interesting on their own. So we showed a general delegation scheme that has these two properties. And I mean, we have some follow-up things that we're thinking about of other applications that I think is interesting. But I mean, I want to throw this out as kind of a really, in my opinion, very interesting open problem. Why is this interesting to have like a delegation scheme that has these two properties beyond the actual example that I'm going to show today of PPAD? So any question before I explain what PPAD is? And I mean, what this means? Good? Okay. Okay, so, just a small point. Actually, to get the PPAD hardness, we need delegation for a hard. I told you to focus on polytime. We need for slightly more than polytime, and therefore our hardness result here, we need to rely on our assumption that I mentioned for slightly super polynomial time adversary. So I said it's hard to distinguish. The assumption for PPAD, it's hard to distinguish with even if you run in time n to the log n. So slightly, so I just wanted to mention. Okay, but importantly, let's explain what PPAD is and what we get. So PPAD is a complexity class, which was defined by Papadimitriou. And what was the point of defining this complexity class? Well, what inspired him is he was interested in the complexity of finding a Nash equilibrium. Okay, so how hard it is to compute a Nash equilibrium. And he defined this class PPAD, for which Nash, the problem of finding a Nash equilibrium, is a member of this class, is a problem in this class. And there have been two very nice works of the Scholastis et al. And Chen et al. That show that actually Nash is PPAD complete. So it's a complete problem in this complexity class. Okay? And this really motivated us to ask the following question. Well, can we prove hardness result for PPAD? Or maybe, so if we can show that there exists some problem in PPAD that is hard, we believe it's hard, then we get hardness of Nash. So people really, game theorists, are interested in this problem. How hard is it to compute a Nash equilibrium? And so then people ask, okay, so how hard is it how is PPAD equal P or not? That's essentially the question. And actually also already in the original work of Papadimitriou, he gave this kind of sense saying that maybe using cryptography we can tackle this problem. So he kind of had this insight that cryptography may be useful. And essentially what we show is that PPAD is hard on average. Okay, so we don't believe Nash is hard on average with respect to some distribution, at least, under the decisional assumption that I mentioned. A super polynomial hardness. So, an adversary that runs in time n to the log n cannot distinguish. So slightly more than just poly hardness, which is the usual cryptographic notion of hardness, but close. Okay, and I just want to mention there's been a lot of actually prior work on this. This is a hot topic in cryptography. But all of them were based on really, really strong assumptions. So IO is probably the most reasonable one of them. But these are also very, very strong assumptions. So
Is it known that those will imply yours? Is it?
Does IO imply like my hardness assumption?
Yeah. In what sense this is?
Oh, okay. No, okay, you're right. No, I should be careful when I say that. I don't know. Does IO imply like standard cryptographic assumptions? Like,
well, I mean,
I'll ask my expert here.
It doesn't imply anything.
Oh, it doesn't. Okay, right. But assuming it's polynomial, things are.
Yeah. It always needs.
Yeah, you need to assume.
Like P different than NP or something.
Well, I mean, are you asking if it implies the hardness of?
Yeah, like
curve-based pairings, or
yes.
Does it imply in general bilinear maps?
No, like does it imply hardness of discrete log?
I think I'm not sure actually. There's these works that construct
Probably
groups
with P
from
different
IO,
than P.
but they rely on groups.
Yeah, I know. I'm not sure what the answer is actually. So let me say.
Like our intuition?
Yeah, sorry. Let me say these are not stronger assumptions, but these are non-falsifiable assumptions. So.
In what sense are non-falsifiable?
So you can't efficiently check. So if you come and tell me, here I broke this assumption, I can't efficiently test whether you indeed broke them or not. That's so in crypto if you come tell me, oh, I have a break for the assumption, I want to be able to efficiently test if you indeed broke or not. In these assumptions, you cannot efficiently test that.
We know that you would not be able.
We don't know how to efficiently test.
Okay, I see.
Yeah.
I think the functional encryption one you actually can.
No, I don't think so, because it's not functional encryption, right? They use a strong variant of it, which I don't think is falsifiable.
I'm not sure. I think it might be reducible to one though.
Really?
One that doesn't exist on multilinear maps, but.
Okay.
And this is the bottom
Yeah.
line.
It's complicated, I guess.
Yeah. Okay. Ran, do you have a question?
Yeah, the PPAD hardness on average, what do you mean by average?
Good.
Like
A distribution, yeah. So what we do, we take an example of a problem in PPAD, and we show that this problem is hard with a specific distribution. Yes, that's what we mean. So I don't know if you ask, okay, I argue that that it's hard to find Nash with respect to what distribution. Is it a natural distribution? I actually don't know how to answer this question.
Okay, but there is some.
There exists some distribution, and yeah, it's not, yeah. It's an efficiently generated distribution, but I don't know, it's not like a natural distribution. I don't know what it even means to be a natural distribution, so.
So if it's hard on average, it doesn't imply that it's just hard?
Yes, exactly.
Okay, so
Yeah, it's hard.
stronger than saying
Yeah,
it's
so
hard.
exactly, it just means,
It's even hard in average.
yeah, it's hard in the worst case for sure, right? That's a,
Okay.
yeah. Okay, so questions about, so this is the statements. Question about the statements of the result. Okay. Okay, so that's, now in the second half of the talk, I want to kind of give you some intuition. So I'm not going to focus on PPAD at all. Actually, the results for PPAD follow pretty immediate from the prior work, without much new work. But the focus, the new techniques come actually from constructing the delegation scheme. The delegation scheme that's publicly verifiable, non-interactive. So this is actually based on two works. The first work, we just constructed a non-interactive publicly verifiable delegation scheme. And then the next work, we made it unambiguous and updatable to get the PPAD hardness. But I'm going to try to kind of combine them in one and tell you kind of the main techniques. Okay, so actually the starting point is started with joint work of Ran and Ron Rothblum. And there what we did, we constructed a similar delegation scheme, but where the CRS, which is not publicly verifiable. So in our case, there was a CRS, there was a secret key corresponding to the CRS, and the verifier needed to know the secret key in order to verify the proof. So to verify the proof, you need not only the proof the same in the CRS, you also need the secret key. Okay, and therefore it's not publicly verifiable. The secret key should remain secret. If everybody knows it, it's not sound anymore. Okay, so only the person who generated this CRS can verify the proofs. Okay, and what we did in this work, we constructed such a non-interactive and privately verifiable delegation scheme under LW, which is a standard cryptographic assumption. Okay, so I want to tell you a little bit about how we did this, because we're going to essentially modify the construction from KRR to make it publicly verifiable. So what is the idea behind that construction? So actually the idea came from a heuristic which was suggested by Yael et al. In '99. And their idea is the following. It's a very, very beautiful idea. They said, you know, MIP, a two-prover interactive proof, or MIP, which was defined in the mid-'80s, actually are great. That we can prove any d-time computation, even non-deterministic time t computation, where the provers, the communication complexity is only polylog t. And everything is very efficiently verified. The overhead of the provers is minimal. They're very, very powerful and great proof systems. However, they rely on the fact that these two provers do not interact. That's really what gives these proof systems their power. Okay, so you should think about like having two suspects. You know, if you lie, if you committed a crime, and there's two of you, we put you in separate rooms, we can interrogate one against the other and kind of find an inconsistency in your versions. If there's only one prover, one cheater, it's much harder to catch him. So that's why it's much easier to work in this proof system. Okay, but we want a delegation scheme where there's one prover. So what was their idea? Their idea was, you know, what if we use what's called fully homomorphic encryption? Actually, at that time, there was no fully homomorphic encryption. They used the language of Peer, but I think it's easier to think of FHE, fully homomorphic encryption, so let's use that for today's talk. So the idea is, suppose you have a fully homomorphic encryption, which today we do under LWE. Now they said, you know what, put encrypt Q1 under one key, and encrypt Q2 under a completely different key. Send both of them to the prover. And the prover, this encryption is homomorphic, so they can do computation under the hood. So given encryption of Q1, you can compute any function of Q1 you want. He'll compute the function that P1 does and get answer 1. To get answer 2, you do the same with this encryption, which is with a completely fresh key. So it's like these are two issues. You can think of it as a box where you have Q1, you can do the computation to get A1, you put A1 there to go to the other box, but you can't see anything in the box. And that's it. And here you have a delegation scheme. And intuitively it seems sound because when you do this computation, you have no idea what Q2 is. This is garbage, it's a ciphertext. It's just a bunch of bits that have no meaning. And when you do A2, you don't know what Q1 is. So it seems a great idea. Okay, so they suggested it, and after that there was a paper with a proof, and the proof was buggy. Long story short, this is not sound. Okay, today we have actually examples. We have an example of a sound MIP and a secure FHE. You put them together, this is not sound. I really would like to tell you more about it because I find it fascinating, but I don't have time. But let me tell you what we did in Kalai. We noticed actually, so we thought it's a really nice heuristic and we really wanted to prove something about it. And this is what we managed to prove. We showed that actually if you start with an MIP that has a strong form of soundness, which is, in other words, secure against what's called no signaling strategies, which are more than just being local. Q1 is only, A1 is only a function of Q1 and A2 is only a function of Q2. If you allow a little bit more, what's called no signaling strategies, which I won't define, but it's a concept that was initiated in the context of quantum mechanics. There's nothing to about quantum in this talk, but it turns out to be relevant. If the MIP is sound, then the delegation, if the MIP is sound against no signaling strategies, then the delegation scheme is sound. And then what we did, we had to work hard to construct an MIP that's secure against no signaling strategies, which we did. Okay, so that was this work. But actually, so our goal is to get the same thing, but with publicly verifiable. Okay, this is clearly, by the way, not publicly verifiable because in order to verify, you need the secret key. You need to open the box, right? So think of Q1 and Q2, think of them sitting in the CRS. Okay, everybody knows it. So I want you guys to prove to me things. I put in my webpage encryptions of queries. By the way, in the MIP, usually the queries do not depend on the computation, only on the runtime of the computation. So you should think these are independent. Suppose I know about the runtime of your computations. I publish my ciphertext of my queries. Now when you come, you want to prove things to me, you give me your computation and your encrypted answers. And what do? I open your encrypted answers and I check. But only I can verify. I need the secret key to verify. Okay, so what was our idea? Let's use a stronger, let's try to use more crypto, a stronger crypto, in order to get public verifiability. And the idea is to use kind of what's like a zero-testable homomorphic encryption. Use a special homomorphic encryption, which will allow us to publicly test this without the secret key. Now, this seems very weird at first, because it seems like you must break semantic security in order to test this publicly. But that was my intuition originally, but this intuition is wrong. You can actually publicly test this without breaking semantic security, the security of the encryption scheme, and I'll explain this, okay? But what I want to mention is that we succeeded. We constructed such an encryption scheme under our assumption, but it's much more complicated than it looks, and I'll tell you the problem.
So you were able to check that A1 and A2 are consistent
without opening.
But then wouldn't the prover be able to check something about Q1 and Q2 without opening?
No, because, good. So, no, okay, good. You have a very good intuition. So Gilad was asking, wait, if anybody can check, then can't you kind of check things about Q1 and Q2 without opening? So we can't our check is very weak. We can check this, but it's so weak that you can't really check anything about Q1 and Q2. And I'll get to it.
You can prove that
you can prove that you can't, yes. We can prove that our scheme is proven to be semantically secure. So, but I'll try to demystify this in a minute, okay? So I know this is now completely seems weird. I'll demystify it. But before I demystify the zero-testable homomorphic encryption, I want to say I wish we can just do like a zero-testable homomorphic encryption that's as beautiful as what's here in this picture. But we couldn't. So let me tell you the drawbacks before I even explain this more deeply, just to explain to you where, because things get much more complicated. So, okay, and not only that, we make it ambiguous because we need unambiguity. So we need unambiguity here. I'll explain what that means. But more importantly, what I want to say is that unfortunately, it's not really, what we managed to get is not really a homomorphic encryption. In our case, the queries here, in order to do homomorphic operation, these queries become really big. And how big or what's the growth? Essentially what happens, in order to be able to do homomorphic operations, we have the query size being small, but then we need to give kind of auxiliary information that will allow you to do this homomorphic. It's not really a fully homomorphic encryption, but it's not even really a homomorphic encryption in the sense that if you need to tell me how much computation you want to do, and I need to give you an auxiliary information large enough that will allow you to do it. And the size of this auxiliary information is like the runtime of the computation. So we managed to get zero-testable homomorphic encryption, but the CRS, or that you can publicly check, at this point just think publicly check, but the CRS here becomes huge, like the time of the computation. Okay, so this is a problem. This is a problem. I promise you a succinct delegation, and now you have a huge CRS. So before I even explain this magic homomorphic encryption, let me say our work, it consists of two parts. Step one, we do construct a publicly verifiable delegation, but with a long CRS. And exactly the reason, I give you the queries, but they become huge. So it's to allow homomorphic computation. So now the CRS size is of length poly t, because the encrypted queries are of length poly t. So that's the first step. And the second step, and this is where the zero-testable homomorphic encryption comes in, and the second step is we bootstrap this part to get a delegation with a short CRS. Okay, so we first have a long CRS, and then we bootstrap to get a short CRS. Okay, and I'm going to tell you a little bit about both steps. Any questions before we continue?
In this bootstrapping step, do you reuse the CRS for the various parts?
So, okay, so yes, I'm going to talk about the bootstrapping step because, before that actually, so we make sure that this is unambiguous, we make sure that this is unambiguous, and if this is unambiguous, we can prove that this is both unambiguous and updatable. The bootstrapping allows us also to get updatability. Okay, but let me...
You get updatability even if the first step wasn't?
Yeah, I don't need the first step. The bootstrap is what kind of allows me to do the updatability, yes. Any other questions? Feel free, by the way, to ask anything, even if... Okay. So I want to say something about this bootstrapping. So this idea of bootstrapping a long CRS to a short CRS has appeared before. It appeared before in the context of knowledge assumptions. So there are works that, it started with Valiant and then Bitansky et al., where they first had a long CRS, delegation for long CRS, under knowledge assumptions, and then they bootstrapped it to delegation with a short CRS. However, their delegation was for non-deterministic computation. I'm talking about deterministic computations. Actually getting a delegation scheme, efficient delegation scheme for NP, let's say just taking a witness and shrinking it, is extremely hard. Okay, we don't know how to do it under standard assumptions. Moreover, there are negative results showing that you'll need to use non-black box reduction, and it seems it's still beyond our ability. It's a great question how to do it. We still don't know how to do it as a community. So what they do, they did manage to, but they said if you have your NP and NP, we can bootstrap. But they really relied on the NP. And bootstrapping P, actually, we don't know. So I a bit lied here. Okay, we actually can't take this as a black box and bootstrap it. And I'll show you why in kind of maybe the next slide after this. So actually what we do, we don't only construct a delegation for P, we almost construct, okay, not almost, but we construct some form of we call it quasi-delegation, because it's not really delegation, but for NP. Okay, so we do give some form of soundness, even for NP, and we bootstrap this. And a quasi-delegation for NP is in particular a delegation for P. If you use P on it, it'll be a real delegation. But I'll say more about this in the next slide. But this is kind of, so we don't actually go from delegation for P with long CRS to delegation for P with a short CRS. Rather, we go to some form of a quasi-delegation for NP, for non-determinism, and we go down, and then we get to delegation for P with a short CRS. Okay, so I didn't say anything how, but maybe now I'm going to explain how it works, and hopefully it'll be more clear. So, but actually, before I just want to mention this idea of quasi-delegation for NP. It already appeared in our work in Kara. We didn't write it this way. But actually what we do in that work is we actually construct a quasi-delegation for NP. And then we show that a quasi-delegation for NP implies in particular delegation for P. So like implicitly, if you go in that work, this is really what's going on.
Can you explain again what's a quasi-delegation?
No, because I will, of course. I didn't explain it at all yet. Okay. It's coming. So, yeah. So what is a quasi-delegation? So I'm not going to explain it formally, but I'll tell you the idea. So, okay, a quasi-delegation, so essentially think of a tableau for a P or NP computation. You can have your witness, you convert it into 3CNF, and you construct a quasi-delegation for this 3CNF. What is a quasi-delegation? it has the same completeness and efficiency that you want, but the soundness is different. The soundness, before you just say, you can't cheat. Here, you can cheat. I'm not saying you can't cheat. Here's our guarantee. Our guarantee is, if there's a cheating prover, I can use him to extract information about the tableau in the following way. I can use him to take any small enough box in the tableau. The number of points in the tableau depends kind of on the query size of an answer size of the MIP. So it's small. It's a locality that we pay for in the efficiency. But you can take any small part of the tableau. You can use this prover to get assignment to this tableau that are locally consistent. So if you claim that if you cheated, I can kind of use you to kind of extract an assignment here and extract an assignment here, not assignment, but like values in the tableau, that these values are consistent with the Turing machine. Okay, so if you want to think of it as, it's easier sometimes to think of it as a circuit because it's a more combinatorial model, but if there's an AND gate here, then the AND is satisfied. So all the local constraints are satisfied on the tableau. So that's one thing a quasi-argument should give you, that you don't have consistency everywhere, which is what you want. What would soundness say? That, well, I can fill in the tableau that will be consistent everywhere, and you'll be consistent with the Y, and hence sound. I can't argue that I can kind of generate this entire tableau consistently, that I cannot, but locally I can. So that's one thing. The other thing, the other property is that, okay, even if I ask this weird rectangle, also I get consistency, but the important thing is that actually the distribution of answers that I get from my extractor, so I have that cheating prover. I use this cheating prover to get an assignment on this, I use it to get an assignment on this. If you look at the distribution he gave me on the intersection, it's the same distribution. So the distribution on the variables here do not depend on the other variables that he was questioned. That's kind of what's called the no signaling, in a sense. Okay, so actually in the work of Kara, what we showed is, we construct, actually you can take what we did, we took the tableau, deterministic or non-deterministic. Actually we didn't care at that point if it's deterministic or not. We convert to 3CNF. We prove that we get this local extractor that's consistent and has kind of this no signaling property that the assignment variables do not depend, the distribution of the assignment don't depend on the other queries. And then we showed if you have this, then actually you get soundness for P. And that's why or for X, and that it was a scale-up version. But essentially, that this implies soundness if the tableau was deterministic for some tableau. I'm lying a little bit.
Every question you ask, the prover will give you a window, like an assignment for some window.
So in other words, you tell me which window you want. I'll generate queries corresponding to this window. I'll ask the prover. I'll look at his answer. It will give me answers corresponding to this window.
And they're consistent in some sense.
They're
not like deterministically consistent.
They're not, but the thing, if you think of it as a circuit of having an AND/OR gates, or in other words, even if you think of the 3CNF, if you have here 3 variables in one clause, the clause will be satisfied. So they're consistent with kind of the local. If you just look at them, they're consistent with each other.
More than that, somehow the margin.
Exactly, and the marginal distribution does not depend on that. Yeah, more than that is important. You're right. But the marginal distribution here doesn't depend. It's the same, no matter if you ask these queries or you ask these queries with it. Okay, so the marginal distribution of the assignment of some variables do not depend on what the other variables are. It's the same distribution. So this is what's called what we call a quasi-delegation. And actually, since the work of Kara, which was for P originally it was even for bounded space. That was done 13. And then we managed to actually, we used the fact that it's a quasi-argument for NP to prove actually you get not only for bounded space, you get for P, you get for RAM, you get for non-deterministic bounded space. So we use this kind of idea of the fact that you're a quasi-argument for NP to get more out of this than just deterministic computations. Okay. So now so we have already a privately verifiable quasi-argument from NP. That's from Kara. And now we can use this to try to do the bootstrapping that we wanted. So Okay, so now what the first thing we do, we use our encryption scheme, our special encryption scheme, our zero-testable encryption scheme to get quasi-delegation, exactly like Kara. We do the same thing as Kara essentially, but use this zero-testable encryption scheme instead of an encryption scheme that you can't check in public.
What is zero-testable?
Oh, good, I didn't really define it. I'm going to define it, but think of it as it's an encryption scheme that you can do the check of consistency between Q and A publicly. Essentially what it means...
But this is an homomorphic encryption. What does it mean for homomorphic encryption?
So I want a homomorphic encryption that will allow you from a query 1 to compute answer 1, and from query 2 to compute answer 2 for completeness. And in addition, I want it to be that you can verify the encrypted queries and encrypted answers, that they're accepting, that the MIP prover would have accepted them. You want to be able to verify them publicly. Our zero-testable encryption, which I didn't define what it is at all, allows you to do that.
But this is one object is encrypted with one key and the other.
Yes, you're right. We need a kind of a multi. Yes.
Otherwise, it's just homomorphic encryption.
You're right. Our zero-testable is what's called multi-key. It's a complicated construct.
Because it's crypto.
It's very complicated. Yeah. So you're right. There's a lot of things in it that I can't. I'm only going to give you a very high-level overview because it's quite complicated. But we do construct this. We do the same thing as we did in Kara, but we managed to use a different cryptographic primitive, what we call zero-testable homomorphic encryption, instead of just a homomorphic encryption. This is quite complex, but we managed to do that to get public verifiability. But whereas in Kara everything was succinct, if you recall correctly, we had a long CRS because of our zero-testable. Unfortunately, we could only construct such an encryption scheme where the queries, if you remember correctly, they expanded. So that gives us a long CRS. We can use this directly to already get soundness for P, for RAM, for non-deterministic bounded space, for long CRS. It's without any modification, like the prior results just work. But we don't want a long CRS. Instead, we want a bootstrap to get a short CRS. So now in the remaining 10 minutes, what I'm going to show you first the bootstrap, how it works, and then I'm going to say a few words about the zero-testable. Okay, and then you get the unambiguous and updatability. Okay, so the bootstrapping actually, as I said, this kind of bootstrapping idea came from the work of Bitansky et al. Bitansky, Chiesa, Canetti, and Tauman. And here's their idea. They said, suppose I have a long computation. For simplicity, think of the configurations as being small, like the small space. In reality, you don't need to assume that. You can use hashes, but I think it's easier to think of it as just small space computations. So suppose you have a very long computation with small space. And for us, if it's very long, the CRS is like the length. It's like T, right? And also for them. So we want a short CRS. What do? We break it up. So suppose you want the CRS to be something like size B. So you break them up into kind of B. You prove only this. And so you only prove them from C0 to CB, you give a proof. From CB to C2B, you give a proof. Very small proofs. And now the CRS you need for this is very small because it's a small computation. So you get a CRS of length B, which is good. Okay, but there's a lot of proofs. The number of proofs is T over B. It's too much. What do? You recurse. What?
What do you do?
Recurse. You do a recursion. So let me explain. Now you look at the following computation. It's smaller. The computation essentially, I wrote it this way, but it's a bit misleading because think of now C0, CB, C2B, and so on. Think about it as non-deterministic advice. Not C0. C0 is the initial. But think of all these as kind of witness. So I want to prove the computation that from C0 I get to CT. That's kind of accept or Y or whatever. And I get as non-deterministic advice the configuration B with a proof, configuration 2B, and a proof that this is, and I just need to check. That's it. Now the point is that when you check, this check is much smaller than B. So this is a non-deterministic computation, but the size is smaller. So we need a smaller CRS, which is wonderful. So the CRS you need here is only length, I don't know, T over B times this, which is very small. So we shorten it. but we didn't shorten it that much, so we recurse. And that's essentially the idea. Okay, so we do it again, we recurse, we take this, we partition it to chunks of b, now b is going to be like, I don't know, like b squared. And we continue with...
Are you losing parameters every time you do that?
That's why we get t to the epsilon. We do lose in parameters.
No, but also in error, not only in...
We don't...
The error accumulates.
The error is negligible, really, so it doesn't, you can, yeah, it doesn't accumulate. You can think of, you should think of it, there's no error. It's so small that it never happens. So the error is not a problem, because the number of times you do this is not that big. It's like, you know, k where b to the k is t. So it's not that huge. But we lose a lot in parameters. So we do lose, and that's why you get only the t to the epsilon. And RRR that I mentioned had the same problem. They also lost in parameters. They did a similar recursion without crypto in a different setting, but it's the same kind of loss in parameters. But what I want to mention that this computation is non-deterministic, and therefore we can't use a result for p with long series. This is NP, and that's the problem. Okay, and in this work, they had a delegation for NP. Okay, with the knowledge assumptions, which are not falsifiable, but they had it and they can use it here. That was kind of why they won, and with P we can't get it.
So you need to, you're given a witness and you check with the witness. This is why it's NP?
Exactly,
What's
because
going to happen in the next step? You get a witness to witness.
yeah, you get a witness to witness, exactly. So you know, it's even worse.
Still an NP?
It's even worse. It's not enough even for this to have an NP delegation. What they needed is an NP delegation with knowledge extraction, what they call SNARK, a succinct, non-interactive argument of knowledge, because you need to be able to extract the witness. So they actually extracted kind of, it's complicated.
But it's not getting worse with the number of iterations.
For them you mean, or?
No, but it's still an NP thing.
Yeah, it's an NP thing.
It's a witness to witness.
Right, it's a witness, yes, it's a.
The first time you do this, you lose the...
Right, but you're right, but the thing is, it's a computational NP, because there's always exists a witness pi1. You need to be, because it's computational. You need to be able not to say there exists, I know a witness, I have it. Then they need knowledge. But our observation here that actually you don't need to extract this entire thing. All you need is like local extraction. So to be able to argue it, I don't need to extract pi1, pi2, all this huge thing. All I need to be able to extract is pi1. And then I extract it, I'm good. Now, separately, I don't need to extract it all at once.
You can forget about
I can forget, yes.
So you reuse what space?
I reuse so how big I extract, that kind of corresponds to the communication complexity of the MIP or the delegation scheme, kind of the same. So if you extract everything, the delegation scheme will be everything. Huge, forget it, it's not worth it. But if you extract a little bit, then you can use delegation with efficiency. So you should think for everything that you extract, you need to pay with the query to a prover. Actually, you need more, like security private number of provers. So the main idea is you don't need soundness, you need local soundness. That suffices. You just need to extract a little bit, and that's good. So now we can use Kara, which is wonderful, but we just need to make it publicly verifiable, and then things go through. So actually, the bootstrapping was just kind of one idea that local soundness suffices, and the rest we just plug in, which is really nice. And then I'll add with Zero-testable, which was kind of. So the idea of using zero-testable encryption already appeared in the work of Guy Rothblum and Omer Panit, but they gave a definition, but they couldn't realize it. They could realize it under they could realize it under multilinear maps. We don't have multilinear maps, so they said if we had what's called clean multilinear maps, which we don't. I mean, we don't know that we have them. At least we don't have candidates. Then we can do this, but we don't have candidates. Okay, but what is the idea? What we really want is an encryption that, so I'm gonna now just focus on the encryption, yes, and you can forget about the rest. Okay, what we want is an encryption that you can recognize, an encryption that you can recognize encryptions of zero. That's really what we need for the public verifiability. But of course, if you can recognize encryptions of zero, this really breaks semantic security, because semantic security says you can't distinguish between encryption 0 and encryption 1. So it's not really what we need. But this is kind of intuitive what we want. But then, we don't need to recognize all encryptions of 0. All we need really is the following guarantee. If you're given some ciphertext C, and it's a homomorphic encryption, right? So you're doing an evaluation. You're computing an evaluation of some function f. If the function f is always 0, doesn't matter what the ciphertext is. So if it's an encryption of 100, 200, the f is just 0 everywhere. Then I want to be able to know that this ciphertext, the value of it is 0. Okay? So I'm only guaranteeing that if I apply the homomorphic computation that's always 0, then the ciphertext is 0. Then the 0 test should pass. It should say 0.
For
No,
every C.
For every C, yeah. For every C, but for f, if you take any C and you apply an f that's always 0, just 0 everywhere, like you apply, I don't know, x squared minus x squared. I don't know, whatever. Then the 0 test should pass. Okay, now this doesn't break semantic security because it doesn't matter what's underneath C, it will pass. It doesn't matter what it is. The point is, this is indeed an encryption of 0, clearly. And you don't learn anything because...
Why didn't I learn anything?
Because the point is this...
F, I learned something about F.
But F is not, sorry. What you encrypted, so C is originally a ciphertext that's encrypted. F is not hidden. So C is a ciphertext. There's a secret message underneath it.
Okay.
Now you apply the homomorphic computation.
Oh, I see.
But this homomorphic computation always gives you 0.
Okay.
Doesn't matter what.
So it is assumed that I know F.
Yes, F is public. Sorry, F is completely public. Okay, so when we do homomorphic computation.
Obviously I should get 0.
Yes.
I know that I'll get
Yeah.
0 because the function.
Exactly.
Okay.
And therefore, then it's okay. So when we do homomorphic computation, usually we think of the computation as public. It's only the ciphertext that's private. We also have what's called private computation, but
Of course it is.
of course,
It's crypto.
it's crypto. But for now, think of F as public. Okay.
Okay.
And also what to make, you can always say 0 test pass. So you also want to say, if you take an F for which you apply and it's not 0, so you take some, I don't know, F and this, let's say the decryption is M. If F and M is not 0, so this ciphertext is not 0, then it should fail.
So the thing is that the decode decodes the cipher without seeing F.
Exactly.
No,
Yes, it doesn't. No, it doesn't.
Zero.
It doesn't see it. It just sees this ciphertext. This is a ciphertext. That's the only thing it sees. This is a succinct
Okay,
ciphertext.
so I don't know the functions that were implied. that
No,
were implied.
exactly. This is F can be huge and this is succinct.
Yeah.
It's like, yes, so you don't know. So the only guarantee we have is if you apply the 0 test on ciphertexts that are non-zero, it will say non-zero, okay, for sure, with probability 1. If you apply them, on the other hand, on ciphertexts which are 0, it may also say non-zero. But if the ciphertexts were obtained by evaluating a function, an all-zero function, on a ciphertext C, then it would pass. And this is exactly what we use.
Aren't you just recording the ciphertext that you...
No, because you can cheat. What do you record in which ciphertext?
that-
C?
Yeah.
What do you want to record there?
That you apply F.
You don't know if you applied F. Someone else gave you C. I mean, if you apply Z, you're just going to encrypt 0 and that's it, or give 0 in the clear.
Okay, so
But-
there's a way of, okay, so someone may encrypt.
Exactly, and I'll tell you how this...
recording that you did.
Exactly. And essentially the way, if you think in your head for a second back to the picture in Kara, where we go for MIP to delegation with 2 encryptions, 2 queried encrypted and 2 answer encrypted. In Kara, what we did, we decrypted everything and we accepted if and only if the MIP prover would have, MIP verifier would have accepted. Here, it can be that the queries and answers, if you look underneath, they're accepting. They may be accepting, but the verifier will reject them. He will only accept if you did kind of the correct thing. If you computed the exact function that you were supposed to. Because if you, and we rely on perfect completeness. Because if you computed the exact function that you were supposed to do, actually you will get the function, if you think of kind of the queries and the verification, the function that computes the answers and computes kind of whether the verifier accepts or not. And I want to think of the verifier accept as being the 0. So that's kind of the 0 test passing. Then if you're honest, then you'll accept for every query. Every query will be 0. And therefore, this kind of the function which combines computing honestly the answers and then doing checking what the verifier would do it's kind of the all zero function. And the verifier will accept. However, if you do something weird, like, well, if you compute a weird function, like, well, if the query is 0, I'm going to do one thing. If the query is something else, I'm going to do another thing. Even if you got the correct answer, the verifier will reject. So the verifier, the only promise is the verifier accepts honest prover if they do things, like a prover if he does things correctly. Even if what's underneath is correct, but he computed in a bad way, not in the honest way, he's probably going to be rejected. Exactly. Okay, so that's kind of the idea behind this. So we construct the zero-testable homomorphic encryption. I feel a bit uncomfortable by. It's a homomorphic encryption, but it's a very weak homomorphic encryption. Like one would think, oh, we have this wonderful homomorphic encryption that's also zero-testable. The homomorphic part is really not wonderful. It's the opposite. So it only supports, and it suffices for us, but it's very weak. It only supports kind of arity 1. You can't kind of combine encryption of Q1, encryption of Q2, and do kind of joint, like binary computations like you can do with encryption. It's really non-succinct like we talked about. And the queries become, if you want to do homomorphic encryption, homomorphic computation, the queries become very long, which is why, we were stuck kind of with a long CRS. So the homomorphic encryption on its own, it's very interesting in this regime, but I feel like to get it, it's not like the homomorphic.
Get it at all.
What?
What's the construction? Is it complicated?
Yes.
Oh no, yada the best part.
I'm not going to show the construction. It's not that complicated, but I'm done. So, so I'm not going to talk about ambiguity, but we get ambiguity. It's kind of nice, too bad. Okay, comparison. So let me just wrap up. So prior work, we got, we used FHE to construct a fully homomorphic encryption to construct this quasi-delegation, and from there got delegation. But this is not publicly verifiable. So the point in this work is to use a special encryption scheme, which is zero-testable, and it has many more properties like multi-key, like Gilad noticed. But anyway, I'm just telling you that I'm hiding things. But because of our special zero-testable encryption, we got a long CRS. And let me just summarize, so just a quick recap. So what we constructed, we used our zero-testable homomorphic encryption to construct a publicly verifiable quasi-argument for NP with a long CRS. Again, quasi-delegation, for NP with a long CRS. And then we bootstrapped it to get publicly verifiable delegation for P. We got the unambiguity and updatability that we wanted that I didn't, the unambiguity I didn't talk at all about. A few open problems. You saw kind of a bit the recursion we did to obtain the bootstrapping. It incurs a loss. That's the reason we go to T to the epsilon and not polylog T. The private verifiable work with Ran and Ron, we got polylog T. We could get it down to polylog T, like as best as we could. So I don't think this, I think maybe one can do a better recursion, and also in this work and in RR possibly. I think it's a great open problem. And as I said, we use a special homomorphic encryption. Another really, really interesting open problem that I think people are now trying to work on is trying to base it under LWE. LWE is another cryptographic assumption that's known to resist quantum attacks. Now people are freaking out with quantum, and they're worried that we'll have quantum machines, so they want to have all cryptography based on quantum resilient, or at least assumption that we don't know how to break using quantum. All the discrete log-based or pairing-based crypto is breakable using quantum computers. So constructing this under a quantum resilient, or at least the assumption that we don't know how to break using quantum, is a great question. Okay, yeah, and then we got the PPAD. Okay, I'm done. Questions? Or? Sorry for not giving you the encryption. Yes, Anne.
So where do you lose the NP? So the first result was for